Okay, in this video we continue the discussion about the different groups of minerals. We were left with a couple of groups that I'd like to discuss with you and also look at from the standpoint of checking hardness and other properties. So I've grouped here a number of silicates. We have basically amphiboles here, some pyroxene, and also these are different examples of different really crystals of the same type of mineral, but this one is distinct and it's different, and it's actually apatite. And then we have talc here and garnet. So there is a distinction we have to make. This mineral here, it's still a silicate, but this one, it's a phosphate, and these are silicates as well. So all of these are silicates, exception made for the apatite, which is a calcium phosphate, which often hosts also fluorium in it. So if you look carefully at the first property, which is the color, you will be in a position to distinguish some minerals clearly. So for example, the garnet, often it's reddish in color, although can be also green, but certainly if you find a variety of garnet that is deep red like this, it's quite easy to recognize it. So color certainly is not the best, but it can be helpful. And so you have here a rock that contains small crystals of garnet, which you can see in the matrix here. So they are included within other minerals. So this is the garnet, usually reddish in color. Quite often is reddish, especially metamorphic rocks. Then we have all these minerals. So we'll take the apatite, we'll put it here, and this it's actually a bit darker in color, and this is why it stands apart from all the others. So this one might be more similar to this mineral here, and also to potentially these other phyllosilicates. So I'm trying to just give you the perspective of the color here and make some classifications based on color. So we've separated already some silicates from the phosphate here, but let's look at the colors. Why am I doing this? Because it's easy to, for example, I would have difficulties, let's say, in distinguishing based on color this mineral here, which is pyroxene, from this other, which is the phosphate, calcium phosphate, so the apatite. So the color is very similar. As you see, we can take two example crystals, so the big one here, and you see it's a very similar green, although here we have more heterogeneity in color, and some deep green colors are well evident, and these could be actually other mineralogy that is forming on top. So it's important to look at the entire crystal here, and you can see that in the section the apatite is more brownish to gray, and definitely that could be, a combination of both pyroxene and apatite in this rock. So it's important to really look at the entire crystal and make sort of an assessment that is based on all the features you can identify, either optical or physical. In this particular case, I think what is certainly diagnostic for the differentiation of a pyroxene from an apatite is the hardness, because if you think at the Mohs scale, you do have essentially that the pyroxene is 6, and then you have your knife in the middle, and the apatite would sit here. So in essence, with the knife you can scratch the surface of the apatite, and also if you try with the pyroxene, you cannot really work this, so you cannot scratch the pyroxene that easily. So that can be a criteria for the distinction. Other aspects is certainly the cleavage. So if you remember, when we talked about the cleavage, we discussed the fact that the cleavage in the pyroxene, you find 2 cleavages. Well, in the apatite usually you have 2 cleavages but they have a different orientation. So quite often when we look at a mineral like this, like a pyroxene, we have like an elongated or prismatic crystal, and this is called the basal part. So this section, it's like a basal section through the crystal, which is orthogonal to the maximum elongation of the crystal, and that basal, it's quite useful because you can see cleavage in the basal. So if I take this larger crystal, for example, if we rotate it, we can see on these basal surfaces there are some steps in here, and so this case, for example, has certainly one step here with this orientation, and then I have other steps with this orientation. So if you look carefully, you realize that they form a 90-degree angle, which is consistent with the fact that the basal surface of a pyroxene usually has 2 cleavages that are roughly at 90 degrees. This does not happen for the apatite. The apatite usually has one cleavage that is parallel to the basal and one on the top part, and so that's why you get the distinction, and you can essentially find out if it's an apatite by looking at the cleavage. Another aspect is that quite often the basal in a pyroxene forms 90 degrees, so it's fairly squared. If you look at this one here, it's even more square, which is a big difference from Amphibole. So if you take Amphibole, you can see the basal here, it's more flattened losange, which is quite characteristic. You can see examples here of the losange as well, which is indicative of a basal of a Amphibole in this particular case. So we haven't talked about the Amphiboles yet, but that's essentially an important distinctive factor. We could mention cleavage also for the Amphibole. You will find 2 cleavages if you look carefully. Like in here, there is some cleavage as well as here, but these cleavages usually do not form a 90 degrees angle or approximately 90 degrees angle. There is usually an acute angle and also obtuse angle, so 126 roughly. So that's a key diagnostic feature also for the Amphibole if compared to the pyroxene. So remember, in terms of number of cleavages on basals, the pyroxene will have 2, the apatite will have 1, and the amphibole will have 2 on the basal section. Other distinguishing factors. Quite often apatite is similar to this other mineral, which is neither a pyroxene or an amphibole. It's also greenish, but many times it's very dark. It can be also black, but also pink and in other colors. But for this specimen, you can see essentially that it does have a fairly similar symmetry. So both of them, both the apatite and the tourmaline, so this is tourmaline, will be hexagonal. So the basal will tend to form those characteristic angles between the faces that give you an hexagonal shape, which is very similar to the druidal quartz. I don't have a specimen here, but if you look it online, a druidal quartz will also have a section that is pseudo-hexagonal. So that is also helpful, so you can clearly see here at least part of an hexagon forming if you consider these faces on the crystal. So I can definitely see an hexagonal shape. The same is true for these. So if I look at the tourmaline will have a similar set of faces that in section form a pseudo-hexagonal crystal. So it's elongated and it's forming an hexagon essentially if I section through it. So the basal will be hexagonal for the tourmaline as well as for apatites. But the difference between the tourmaline and the apatite is certainly the hardness. So same procedure, you can scratch it quite easily with the knife, but you cannot really scratch easily the tourmaline because tourmaline is really hard. In fact, it's often used as a gemstone because of its nice greenish color and the fact that it's really hard. So it's also quite hard, it exceeds the 7, so it's even harder than quartz, which is quite interesting. So if you try to use and get sort of a scratch, you will realize you can leave actually pieces of the ceramic plate on a pointy edge of the tourmaline because it's actually harder or very close to, in terms of hardness, to the ceramic plate, which is 7.5 up to 8 in some cases. So its hardness is actually comparable to this other mineral, which is the garnet. Of course, if we have to differentiate garnet from the tourmaline without really referring to color, hardness could not be really a good diagnostic feature with the tools that we have because both the garnet and the tourmaline are really hard minerals, so they are comparable or even harder than quartz. But certainly for the garnet it's easy because of the symmetry, so quite often you will see pseudo-spherical crystals like this, which are dodecahedrons, and they have faces, but since this mineral is cubic, so it's not hexagonal, the tourmalines are cyclosilicates of boron. Instead, this is a garnet, usually is a ferromagnesium silicate, and it's cubic, so its structure is cubic, and because of that it tends to form equant crystals or stubby crystals like this, and so easy to distinguish from tourmaline based on the symmetry when the crystals form in a neohedral form, like this example here. So of course we have a variety of ways in which a mineral can crystallize. You will find also cases in which the pyroxene grows in aggregates like this, so you can describe this specimen as an aggregate of multiple pyroxenes. But still you can recognize the 90 degrees angle on the faces, so it's quite, although there is a different appearance from these two crystals, I can still see, if I look carefully at the tiny crystals in this specimen, that the symmetry is very similar. That's a good indication that we are dealing with a pyroxene. Probably we will look at the magnified version of these two to illustrate better the symmetry relationships between faces and the angles that you find, which are quite useful. See, there is a section here. This is quite a square as well. Nothing like the amphibole here. You can see that this is definitely not a square section, so this is like a flat elongated crystal, and often the amphibole will have very characteristic striations on its faces, which can be also useful for the identification of the crystal. You don't see that for the pyroxene. Other things, still see here in this small piece of apatite the hexagonal shape of the crystal. Many times also you can see some iridescence colors, which actually mark a distinction, optical distinction between the pyroxene. So it does have also different luster. I think the example here of apatite is much more glassy, and that is also helpful, I think, for the recognition and distinction of these two crystals or two minerals. I think I'm left only with these last minerals here. So we have an example here of barite, so barium sulfate. Usually if you are in a lab, it's quite easy to recognize barite because it's really heavy. So barium sits low in the periodic table of elements, so it does have a relatively large atomic mass, and because of that it's quite heavy. So it's the feeling, it's very similar to holding galena or other oxides or sulfides, as we discussed earlier in this lab. How do you differentiate these barite from other similar minerals such as carbonates? So if we take the calcite here, you can see the color is very, very similar. I would say that calcite is more translucent, so light can go through it more easily if compared to barite. Barite also does have this characteristic fibrous aspect, so it's looking like there are intergrowths of barite crystals which are quite characteristic, and also one distinguishing feature, I think, it's the acid. So barite is a sulfate, it will not react to HCl. So we can do a quick test and see if there is any reaction, and I definitely don't see any major reaction in this case. So that's definitely something that it's important to consider. I think barite is also harder than a carbonate. So if we try to scratch with this, so with the pin nail, we'll be able to do it. If we scratch with the coin, we also are able to do it. So it's comparable, but slightly harder than a carbonate. So the carbonate can be it's much more easy to scratch the carbonate with a copper coin, and sometimes carbonate can even scratch it with the fingernail, whereas in this case it's much harder. But yeah, they are comparable, I think. So hardness is probably not the best distinguishing factor. Yes, the other minerals are phyllosilicates. So if we take this mineral here and this one here, we can try to see if we can scratch them, continuing with what we were discussing about the hardness. And definitely I can scratch this flake of muscovite. And this one looks like muscovite, but yeah, it's much softer. I can really break apart small pieces of these, and so this actually has a more sort of greasy feeling, and it's very easy to break. And so these crystals are not muscovite, are actually talc. So this is how talc looks like. It's translucent, and it does have a perlaceous luster, which can be confused with this more metallic luster of the muscovite. But the hardness, as you can see, pieces of talc falling off my fingers, is certainly a good criteria to identify this particular mineral, which in this case is hosted in a talc schist, so it's also a metamorphic mineral, quite often similarly to muscovite, although muscovite can occur also, as we will see in the next lab, in intrusive rocks. So definitely the hardness in this case will be a critical factor in distinguishing between muscovite and talc, which is much softer than the muscovite. So I think this concludes this initial lab in which we were trying to group minerals. In the next one we will try to clarify the nomenclature of some of these specimens, and also look at other things such as measuring density, which is another test that can be practiced to differentiate the minerals. So I will catch up in the next discussion.